All right, the topic is vector functions and parametric equations. So let me start with some nice example to illustrate the idea of the topic. So here is a unit circle. So unit circle consists of points with distance 1 from the origin. So for this curve, we want to use some certain parameter to get parametric equation. Let me pick some point, say point P. So then we have x coordinate and then y coordinate like this. Okay. Once you draw a line joining the origin and this P, we have right triangle, and let me call this theta. So we have theta, the angle between this positive x-axis and the line OP. So using this right triangle, you can express x and y in terms of theta. So x is hypotenuse times cosine theta, or simply cosine theta, and y, this y coordinate is again hypotenuse times sine theta. Good. So we want to express a unit circle in terms of parameter theta. So unit circle is simply the set of all points of the form here. Theta is an angle between 0 and 360. Okay, so you let theta be any number and collect all points, cosine theta, sine theta, then you will retrieve all the points on the unit circle. So in that sense, this represents the unit circle. Okay, so that's the idea. So we use a parameter. In this case, theta or t, to write a parametric equation. So this theta is also good. If you use t, then we have a parametric equation. X component is cosine t, and y component is sine t. Here, t is between 0 to 360. Again, by letting t be any number, you can express all the points on the unit circle. So you are collecting all the points of this form where t can be any number between 0 and 360. Okay, so we can continue to find vector function for the unit circle. So we want to find a vector function. Well, the idea is nothing new. Again, for this point P, we can take vector OP. And in the previous slide, we expressed this point P in terms of cosine and sine. So for this vector OP, x comma y, we expressed x in terms of cosine and sine t for this y component. You simply form a vector with those components. And you can name this, well, let me pick R but it doesn't matter. Depending on your preference, you can call this A of t, S of t. This is just the naming. Here, t can be any number between 0 and 360. Okay, so basically the same idea, but let me emphasize how those vectors represent unit circle. So we represent the unit circle by, well, again, unit circle consists of points. So we represent the unit circle by the collection of terminal points of vectors. So let me draw. So we have vector OP like this. And to represent the unit circle, you can think of terminal points. So you let t be any number. So t is the angle. You let t be any number. And then you collect all the terminal points of such vectors. Then you will represent the unit circle. Terminal points of vectors, assuming the initial points are at the origin. So that's assumption. Whenever you use a vector function to represent some curve, that's the assumption. We want to collect all terminal points of vectors, assuming the initial points are exactly at the origin. All right, so quick example to find vector equations and parameter equations and Cartesian equations and draw the curves. All right, the first example is given by parametric equation. So x component is function in t, which is t minus 3, and y component is a function in t as well. So this is actually already parametric equation. And you can form vectors to write vector equation. So you can form t minus 3, comma, to t minus 1 to have a vector equation. So basically the same idea. And then to sketch the graph, we need to know we need to find Cartesian equation. To find Cartesian equation, you eliminate the parameter t. Well, from the first equation, you solve this for t. So t is x plus 3. You plug that back into this equation. So y equals 2 times t. Let me use color. So here, you are replacing this t by this t. So 2 times x plus 3 minus 1. That's it. And then once you simplify this, you will get a Cartesian equation. So 2x plus 5. This is Cartesian equation. Well, this name comes from French mathematician Descartes. And once we have this, we can sketch the graph. This guy has slope 2 and y-intercept 5. It's just a straight line. Okay. Let me use this graph to, again, emphasize how we use vector equation to represent this curve. Remember, when we use vector equation, we are collecting all the terminal points of vector. So we are thinking of vector, well, actually infinitely many vectors like this, and then we are collecting terminal points of those guys to represent this curve, assuming the origin is the initial points of all such vectors. Okay, second example. Well, this is already in vector equation, and you take x component, y component to get parametric equation. So parametric equation is going to be x component, y component. Quite simple. All right, and then Cartesian equation. If you eliminate t, then you will get a Cartesian equation. From this, we have, well, I mean, if you solve this for t, t is x plus 3. If you plug that back into this y, we have x plus 3 squared minus 1. We see the vertex is negative 3, comma 1. So 1, 2, 3. So from this Cartesian equation, we know how to plot the curve. The vertex is negative 3, comma 1. So we have vertex like that. If t is any number, we need to take the entire parabola, but some restriction is given. Say t is from negative 1 to 3. Suppose we have this restriction, then we need to take some portion of this parabola. So for this first value, t equals negative 1. If you plug that into this x, we have x equals negative 4. And if you plug that into this y, we have 0. So we have negative 4, comma 0, which is this one of x-intercept. And then you can plug 3 to have, well, here, if you plug t equals 3, x is 0, and y equals negative 1. Sorry, if you plug 3, 9 minus 1, which is 8, 0, comma 8. So you will take portion like this. You can talk about the direction as well. As t grows, you are following this direction. So as t, so this is the direction as t grows.